Hi everyone, welcome to today's lecture in the TJ Machine Learning Club. Samir and I will be going through generative algorithms, and hopefully you guys get a good understanding of the main generative algorithms by the end of this video. As always, please type any questions in the chat and we will do our best to answer. First, let's start by looking at these three pictures. To me, and probably most of you, these pictures look extremely realistic, but they were actually artificially generated. And you can see many more of these on a website called thispersondoesnotexist.com. We will get started by looking at an architecture called the Variational autoencoder. Since it is essentially an extension of the regular autoencoder, we will start by providing a short review of autoencoders in general. First, recall that an autoencoder takes in an input, which could be an image or something else, and stores some learned information in the bottleneck layer, or the latent layer, which finally leads back to the reproduction of the original input, as you can see in the image provided. And this makes the training process for an autoencoder completely unsupervised, because all you need is an input. And to train it, you use some sort of reconstruction loss to see how well your reconstruction x hat is compared to the original x value. And this can be done in several ways. However, using the mean absolute error, as shown on the slide, is one of the simplest loss functions that can see how close your reconstruction is. Unfortunately, general autoencoders are not capable of generating new images or features, and we will see why this is the case on the next slide. In an autoencoder with a regular bottleneck layer, as shown on the previous slide, the values in that layer can be any random number falling in any random distribution, as shown by the top image in this slide. However, when we get to the stage of generating images and pass in random values in place of the bottleneck layer, then most likely we will end up with some random image that makes no sense to us, because our numbers could easily fall outside that bottleneck distribution. So the key to fixing this is to restrict the distribution of the bottleneck layer values to a distribution that we can define mathematically, such as the standard normal distribution. And by doing this, we can randomly sample from the fixed distribution to generate more realistic images. So in this slide, I've shown the general structure for a variational autoencoder. And you can see that it's pretty much the same as before, except for the middle layer, which I'll be calling the latent layer. Unlike before, the latent layer is not just one fully connected layer. Instead, it's a probabilistic layer. Let's step through each portion of the architecture. So first, there's an input image x, which is passed through the encoder. The encoder stores the image by encoding the image features in terms of a mean and standard deviation vector. While training, we force these mean and sigma vectors to fall in a standard normal or Gaussian distribution. And the final latent vector z is sampled from the given mu and sigma values. Finally, the decoder denoted as p of x given z decodes the information in z to reconstruct the original image, making the overall process, once again, unsupervised. Before moving on to the loss functions, let me address one error that we will run into when training the model. Since the vector z in the latent space is a stochastic node, we will not be able to do backpropagation through that node. And the reason z is stochastic is because its values are randomly selected from a standard Gaussian distribution. Since gradient descent is an iterative process, the gradient will not pass through the stochastic node. So somehow, we must make the z value deterministic in order to train the model successfully. And to do this, we will use a trick known as the reparameterization trick. The reparameterization trick is actually pretty simple, but it's an intelligent way to make z a deterministic node. So the main issue that we had before was that we were directly sampling z from the normal distribution with sigma and mu defined from the previous layer. Now with this method, the new method, you can see that z is no longer stochastic because we do the sampling in an external node defined by epsilon. So if we define epsilon by sampling values from a standard normal distribution, which means it's the same as a Gaussian distribution with the mean of 0 and standard deviation or variance of 1, and then if we take this epsilon value and multiply that by the sigma vector and add the mu vector, that's essentially the same thing as what we were doing before. Or in other words, that's the same thing as sampling z directly from a normal distribution. So the difference is, using this process, Z is no longer the stochastic node. Instead, epsilon is. However, we will not backpropagate our weights through epsilon, so now our problem is solved because Z is now a deterministic node. So with this, we're able to train our model and backpropagate the gradients to train the entire autoencoder. So next we'll move on to the loss functions to see how we can set specific objectives so that our model will learn specific features. Now let's see the loss functions that we will use to help us train the variational autoencoder. Again, since the main objective of an autoencoder is to be able to produce accurate reconstructions, we set the loss function to either a mean absolute error or mean squared error or something along those lines. However, the new part of this is the Kullback-Leibler divergence loss. Remember that one of the main parts that make a variational autoencoder work is the fact that the latent space values fall in a standard normal distribution, specifically the mu vector and the sigma vector. So while training, we need to somehow force the model to do this. And in general, the KL loss, or the Kullback-Leibler divergence loss, is used for measuring the distance between two probability distributions, and it's a pretty complex formula. But when finding the distance from a standard normal distribution in particular, it simplifies pretty nicely, as you can see on the screen. So you can see that I've provided both the loss functions on this slide. And if we train the variational autoencoder by minimizing both of these loss functions, we can successfully train a variational autoencoder to produce accurate reconstructions and have a latent space and keep the latent space mu and sigma values in a normal distribution. There's one small change that people use when training their autoencoders, and that is to write everything in terms of log of sigma squared, or in other words, the log variance term. Doing this just helps speed up the training process and helps the model learn more important features. You can try substituting the log of sigma squared back into this equation, and you should get the exact same loss function that I showed on the previous slide. Now I'll go through each section of the variational autoencoder, starting with the encoder. Let's say our input is some image x. What the encoder does is it compresses the image into its main features, which are stored in mu and sigma vectors. This can be done through a series of convolutional layers or fully connected dense layers. However, in general, using convolutional layers will help extract more complex features, but it may make building the decoder a little bit more difficult, as we'll see in a couple of slides. So now that we know how to get the latent vectors, let's see what exactly the latent space is made up of. From the encoder, we have the mu and sigma vectors, and let's assume that they have a length k. So getting the final vector z is pretty simple from here. All we have to do is sample from a normal distribution with the mu and sigma values specified in the previous layer. And this creates a z vector with k values in it. So the simplest way to think about this is to imagine that each of these k values in the z vector are representing a different features. For example, let's say you are passing in images of faces through the encoder. So one particular value in the z dimension might represent the skin color, and another might represent facial expression or something along those lines. And the goal is to make the model store only the most important features from the input image due to the limited size of the z vector. So let's go into some more detail on how one should go about choosing the right dimension of the latent space. Choosing the right k value can be tricky, but it's important if we want to be able to generate realistic images. If the k value is too small, then the model will not learn any important features. And as a result, the reconstructions will be poor and the generated images will also not look realistic at all. On the contrary, if the k value is too large, the model will not actually learn any general features. It may just memorize pixel values, which is pretty much a waste. If your reconstructions are too accurate, that may be a sign of a large k value, because values are just being memorized from the input image x. Although the reconstructions might be good in this case, the generated images will still not be recognizable. And the key is to get just the right value for k, so that there's enough space to store important features while still forcing the model to learn general image features and not memorizing pixel values. So some experimentation may be required to find that optimal k value. Now let's take a look at the decoder. we already know how to get to the latent vector z. And the goal is to be able to store the most important features in z because the decoder has to be able to recreate x or whatever the input image was by only looking at the z vector. That's also why the z vector is called the latent vector, because it stores hidden information from the original input image. So as you can see from this diagram on the slide, the decoder does not connect to any part of the encoder. So it has to do everything based on the compressed z vector. Actually constructing the decoder is pretty trivial, since it is just the exact reverse of the encoder. So let's say you use convolutional layers in your encoder, then you would have to put transposed convolutional layers in your decoder until you get back to the original image dimensions. That's basically it for the structure of a variational autoencoder. Probably one of the most important aspects of a variational autoencoder is the latent space. So it's important to have a good understanding of what exactly is the purpose of the latent space and what you can see from that latent space distribution. So as I've mentioned earlier, the latent space z vector, each item in that vector is coding for a specific feature. And because that's a compressed version of that original image, it only stores the most important features of whatever that input image was. And what's interesting is that by changing one value of this latent space z vector, you can see what type of feature it's actually encoding. So for example, if you take a look at this image that we have over here, by changing one of the latent space values, you can see how you can remove the eyeglasses off of somebody's face. Or over here, by changing one of the latent space values, they're gradually changing the gender of the person. So you can use certain techniques like that to modify your data set, and they've used this technique to create better data sets because they're able to modify images to better represent a general population. I'll just go over a couple more applications of variational autoencoders. And I just mentioned that you can create more fair data sets by manipulating and analyzing the latent space. But there's also another interesting application, which is doing semi-supervised training for a variational autoencoder. So let's say there's an instance where you have a lot of images, but only a handful of those images are actually labeled. So you still want to make advantage of all of those unlabeled images. And the way you do that is to pass all of those unlabeled images through a variational autoencoder. Because then the first few layers in the encoder will still learn important features from these images. And then after that, you would take those first few layers from the encoder and then use those layers to actually create a prediction with the labels that you, for the small handful of images that you actually do have labels for. So that will help you that'll help you make use of more images. And the thing that benefits the most is because it's really hard to find, sometimes it can be hard to find images that are all labeled. So in this case, you don't need that many labeled images. And finally, another cool application that was actually pretty recently done by Google's DeepMind was a project called Draw, which is a recurrent neural network for image generation. So basically, they were able to draw images. And they used variational autoencoders along with reinforcement learning to accomplish this complex task. Finally, let's see how to actually generate images. The encoder does not play a role in the generation process. Once the variational autoencoder has been trained, all you need is the decoder. Before, we used to pass in the z vector, which would output the reconstruction image. Now to generate new images, we can just input random values instead of z. In addition, because we restricted the latent space values to a standard normal distribution using the Kullback-Leibler divergence loss, we just have to sample k random values from that distribution, or the normal distribution, to generate a new image. So every time we sample new random values, we will get a different image, as you can see from the flowchart in this slide. So that's it for variational autoencoders, but before you start learning about generative adversarial networks, or GANs, take a look at these generated images. What do you notice about them? Do they look a little bit strange to you? Most likely you thought that they were not very realistic, even though that you can tell that there are faces. One of the reasons that autoencoders produce this blurry output is because they are trained to reduce the average pixel-wise difference, which these pictures are doing a pretty good job with. However, the benefit of GANs are that they can produce pictures that are more sharp and realistic, as you saw on the title slide. As you learn more about GANs, see if you can see the pros and cons of both of these types of generative algorithms.
We will now be talking about generative adversarial networks, or GANs for short, which is still a relatively new topic as it was invented by Ian Goodfellow in 2014. As many of you may already know, generative adversarial networks are used to generate realistic images, such as the images that you saw on the title slide. A generative adversarial network is composed of two parts, a generator and a discriminator. The generator generates a distribution of images that accurately samples a training distribution, while the discriminator tries to differentiate between fake and real images. To illustrate this, consider an example where there is a group of counterfeiters that are printing fake money, and there are police that are trying to distinguish the fake money from the real money. Over time, the counterfeiters will get better at generating the fake money, as it will end up looking very realistic, but the police will also get better in distinguishing the counterfeit money from the real money. In this scenario, the counterfeiters serve as a generator and the police serve as a discriminator. We can also see how a generator and a discriminator are opposing sides in a game, which is known as a minimax game, as the discriminator wants to maximize the distance of the real distribution from the generated distribution, while the generator wants to minimize the difference. And we can also see that training a GAN is an unsupervised process, as the images that are being generated are used to model a real data distribution. Lastly, we can see on the image to the right how a generator and a discriminator alternate in adjusting their weights. So now that we have a basic understanding of GANs, let's look more in depth into the generator. The generator first takes in as input a vector of random noise. The random input vector will allow the generator to generate more diverse images, but also shows that the goal of the generative adversarial network is to transform a simple distribution, such as a random distribution, to a more complex distribution. It then feeds through a neural network and produces an image. This image will then go into the discriminator network, and depending on how real or fake the discriminator classifies these images, the generator will update its weights in order to produce a more realistic image. So now that we know how a generator can produce an image, how does the discriminator distinguish between a fake image from a real image? The discriminator is actually a binary classification neural network, where 50% of the time it is fed a real image from a real dataset, while the other half the time it is fed fake images produced from the generator. The goal of the discriminator is to output a high probability when the input image is real, and a low probability if the input image is fake. So now that we have a general understanding of how the generator and the discriminator work, let's consider the process of training a GAN. To preface, training a GAN is very hard and unstable because we are training two different networks at the same time. Thus, having a better training process and using better loss functions when training GANs is an active area of research. During each iteration of training, for case steps, we will sample M noise samples and M real data points. There isn't a consensus on what is a valid value of K, as some find K equal 1, working just fine as it's stable, while others train with K greater than 1. This is an issue in training because of stability. Regardless, the discriminator is trained through a process of gradient ascent. So here we see the binary cross-entropy function, where the log of d of x is the log likelihood of x being a real image, while the log of 1 minus d of g of z represents how fake a discriminator perceives an image produced by the generator from random noise vector z of I. Intuitively, the discriminator wants to maximize the difference between the distance of the real data distribution and the generated data distribution. Thus, this is called gradient ascent, because the discriminator wants to maximize this expression. Now, we want to train the generator. We again sample a mini batch of M noise samples, and it wants to minimize the log likelihood of the discriminator's probability of a generated image produced from random vector z of I being fake. Because the generator's goal is to produce more realistic images, the generator wants to minimize this expression. Now that we know the training process for GANs, here are the results of a trained GAN producing images based on the CFAR10 dataset, and how they compare to actual images in the dataset. As you can tell, these images are very blurry, and a human can easily tell that these images are fake. So now we'll investigate how to produce more realistic images. The vanilla GAN that generated the images in the previous slide contained only linear layers. As a result, there is a simple modification to a GAN architecture we can make, which will produce much better results. By replacing the linear layers, which we used before, with convolutional layers in the generator and the discriminator, the results of the GAN are much better. The main motivation behind this is that convolutional neural networks just yield much better results in computer vision tasks. However, when implementing DC GANs, or deep convolutional GANs, there are a few guidelines to follow that were proposed when the architecture was first introduced to better improve the training process. First, replace pooling layers with strided convolutions in the discriminator and use fractional strided convolutions for the generator. You should also use batch norm in both the generator and the discriminator. You should also remove fully connected hidden layers in deeper architectures. For activation functions, always use the ReLU function in the generator, with the exception of the final layer, where you should use the hyperbolic tangent function, and use the leaky ReLU activation function in the discriminator. And as you can see in the bottom right image of the slide, the images of bedrooms generated by a deep convolutional GAN are far more realistic than the images we've seen before. I've mentioned before that the training process of GANs is very unstable, but let's now go into a little bit more detail of what I mean. The first problem of the training process is mode collapse, and it arises when the discriminator overpowers the generator. This results in the generator starting to produce similar images, and there isn't much variety. And this is illustrated in the image on the bottom left, as initially there's a wide variety of MNIST-like numbers that the GAN is generating, but over time, the images that are produced are of a single class. Another problem is that the binary cross entropy loss function that is used in training GAN will likely lead to the vanishing gradient problem, where the weights of the discriminator and the generator will barely be updated, potentially causing the networks to stop training. A popular architecture that tries to handle these problems is the Wasserstein GAN, as it improves stability and uses a better loss function than a vanilla GAN. The Wasserstein GAN uses the Earth mover's distance to estimate how different two distributions are. And the Earth mover's distance is the amount of effort that it takes to transform a generated distribution into the real distribution. This lends to the first major change to the GAN architecture, is that the Wasserstein GAN doesn't use a discriminator, but rather it uses a critic network. Unlike the discriminator, which outputs a probability of an image being real, the critic outputs any continuous real value, which is interpreted as how real any image is. Thus, the new Wasserstein loss is E of C of x minus E of C of G of z, where x is a real image and G of z is an image produced from random vector z from the generator. And this is still a mini-max game, because the generator wants to minimize the value of this expression, while the critic wants to maximize the distance between the real distribution and the fake distribution. So the discriminator's binary cross-entropy loss is bounded between the values of 0 and 1, while the critic's loss is unbounded, making it better. This new loss function helps deal with both mode collapse and the vanishing gradient problems. However, for a Wasserstein GAN to work properly, it needs to be 1L continuous, or 1 Lipschitz continuous, which means that the absolute value of the slope of the gradient is never greater than 1. And this continues to make the training of a GAN more stable, because it will ensure that the Earth mover's distance is a valid comparison of the generated distribution and the real distribution. Other popular improvements of a normal GAN is also the LS GAN, which is the least squares GAN. There are a lot of cool applications of GANs, and here are some of the most popular applications. The first is a conditional GAN, which generates an image based on some condition like a class label. In this case, the training dataset also needs to have a label for what the class is. Another popular application is translating between domains, which can be done using pix-to-pix and cycle GANs. Stack GANs are given a sentence, and the output is a generated image of the sentence. And you can see a couple examples of this architecture on the bottom right. Lastly, the style GAN is the current state-of-the-art GAN architecture, which can produce very realistic, diverse, and high-resolution images, and have the ability to have allows the ability to have more control over the features that are in the image. Lastly, if you want to practice implementing a GAN on a real dataset, there's currently an ongoing Kaggle competition with the goal of producing paintings with the style of Claude Monet. Thank you.